Hello folks, it's been a while since I've recorded a video because a lot of my spare time over the past few months has been devoted towards building an application that can analyze materials across hundreds or thousands of GPUs. I developed this code as part of a team's effort towards a Gordon Bell Award through the Supercomputing Conference, and along the way I learned a lot of new things, honed some other skills, and in some cases, remembered why I tend to develop software in a particular way to make building these kinds of applications as a team and in a way that you can understand where and how they work is simpler. And a lot of the core of that is how I write the application such that when I run it at a large scale or run it in generally a series of experiments, I can go back through and understand what's happening in the application, making it easy that I could go back and be able to say, monitor its activity over time, or on each of the GPU nodes, or track the scientific progress in a way that I didn't necessarily have to envision exactly what plots I wanted at the beginning, but I had the information available such that it was readily accessible, organized, and developed in a way that I could easily build those plots together. And effectively, the strategy that I use to do this follows under a few different strategies and results in a directory of what you'll see kind of on the left here. I'm able to take all of my experiments. Here, I've got a few that we ran on different numbers of nodes on the Polaris supercomputer at Argonne National Laboratory. And for them, I've got an output of a few different snapshots of measurements on how the supercomputer is working. I have performance logs of the utilization of each node, what I was able to do to gather these plots. I have a measurement of what the scientific output was, recorded in a database that I could output to a format that I can read in and build these kinds of plots atop of them. Or I have a tracking of what each node was doing at any individual time that I can use to track and make sure that at any point in the application, there are very few of these little white specks, which are parts where a node is not being used where it should be. And you can see we only have a few of them. So all of this requires being able to construct the application in such a way that each of these different facets of information is written out, and ideally written out separately from each other, such that different people can work on studying different aspects of the outcome of that simulation and be able to come up with a rich picture of whether everything was working the way you hoped it would. So like I said, this isn't something that happens by accident. It's something that I've developed over the course of time with working with a lot of different people and follows a few kind of typical approaches. And we'll go through them separately. And since I always generally write notes for these applications, I thought might as well put them on a PowerPoint slide to get a visual aid. The first part of the process is ensuring that you set up your application such that all of your experiments are isolated from each other. That means your applications its behavior is not changed by editing the Python file, which, unless you're very diligent about using Git version control, it'll be difficult to map the changes you've made to that file to the outcome of the experiment. You want to make sure that all of them run in their own directory, such that no experiment writes to the same data file and you have to demunge them later. And you can take all of the applications from that single experiment and combine them together. So let's talk through each of these applications and how we or these ideas and how we actually realize them. So with that, we're going to go to the application that I've been writing. I'll send you the link to all of this, but it's a code called Mock Generation at Scale, MOFA for short, though yes, the name of the application GitHub doesn't necessarily map to the name MOFA. It's just Spanish for taunt, and I thought that was a fantastic name, so we stuck with it as a team. Now, the core of the application of how we actually launch it looks like this. This is my run script for running on a high-performance computing system. This is my test version of the application. You'll know that because it only runs on 8 nodes, so 32 GPUs. and it only runs for 30 minutes. This is what I use to just make sure everything is functioning properly. And I have it set up that each of these experiments will run completely isolated from each other. Any of the tools that need to be performed for kind of the run to support itself, like launching this MPS daemon, which allows multiple tasks to share the same NVIDIA GPU, happens in here. The Redis server that's used to communicate is launched within the job, such that there isn't any real possibility for multiple runs of the same experiment to interfere with each other on the software level. The other thing that happens is you'll note I'm calling a Python function with a lot of these argparse arguments, that each of these define different aspects of how the application behaves. And I have them written out as arguments rather than as points within a file that I change, such that I have a clear record. And we'll show you a little bit more on where that comes into play. So jumping over to the software, all of those command line flags are read by the argparse library. So you can see here I've documented what their default values are. I've provided default values, described how that affects the application, grouped them by what part of the behavior it changes. For instance, whether or not I run lamps using the global file system to store the output files, or whether I write them directly to memory, shouldn't change the science directly, so I don't lump it in together with things that have to do with how my simulations happen. In this way, I can keep things logically together. Different people can know, or different people on the team can know where to go look if they want to study a particular part of the application. They don't have to demunge it from everything else. Once I have this arguments, I can take them, I can read them in, and write them back out to a file in JSON format, such that that application has a record of all of the settings that I provided to it, written in that output directory. Now, the output directory itself looks like this. What I do is I take those input settings and I write perhaps a few details about them, like I write out which configuration of supercomputer I'm running on, when it started, and I also write a hash function. I take the JSON file, I write it to a string, I encode that string as a series of bits. That information I can run through a hasher such that I can create a unique identifier, or something that's generally expected to be unique, describing the run. That allows me to take and ensure if I run the same experiment over multiple times, it's very easy to detect which runs use the same configuration. So that is the output directory. So now I've got a place to put all my files. And when I'm, say, having an application which uses a temporary or a set of directories on the supercomputer, or sorry, uses its own set of directories independently, like my workflow engine parcel writes its own output files. I ensure that those output files are written to that run directory such that everything is nicely co-located together. I can easily find the files that belong to the run, and I know if they're in that folder, there are only files from that run exist in the single run folder. So that's output files. Let's see, what else did I want to talk about? Yeah, co-locating logs. So that should cover all of it. We can see that any place that I need an output file, like perhaps when I'm running my simulation codes, they're going to write some files to disk. If I want to persist them, I ensure that those output files are in a subdirectory of the run folder. Everything is nice and happily crammed together to make it easy to analyze later, and also very easy to delete files from a run that failed and I no longer want to debug it. Great, so that's part one. We've, just to recap, described how I use argparse to be able to ensure that my experiments don't require editing the Python files, which one, diminishes the chance that two programs executing at the same time, if I'm running two experiments at once, aren't reading from the same file and therefore not doing what I expected them to. But it also ensures that I can document what those input files are. I can dump the configuration to disk afterwards and everything's happy. I put all of those files and anything else to deal with that run in the same folder such that I can go back and analyze it later. And this is the way that I construct basically all my experiments, be it things that run locally on my desktop on maybe a few CPU cores, or things like this application, which run on thousands of GPUs. This is just a nice way of ensuring that my experiments stay separate from each other. Now, one thing I will note, I'm eventually going to want to, or trying to move away from argparse. Having input files like the one I showed you, and I'll go back to this screen here, are a bit annoying because I can't easily leave like comments in this file here. I can't write a comment after this slash, which is the line continuation symbol for bash. Bash won't let me do that, so I can't leave comments here. I could leave them up at the top, but I kind of like my comments being nearby the code that they're commenting. So I still don't like this a lot. One of my colleagues, Greg, tends to write his input files such that they do use argparse, but one of the options is a path to a file from which I read parameters, which I think is pretty clever. I can actually point you to where one of the examples of how Greg does things that I think I can learn from personally. But yeah, that's the first part set up. So once I have this directory, the next question is, what do I run in it and how? And that, going back to the notes that I had for this episode, follow a few different concepts. The first of which is, what type of file do I write in? Now, I typically write in 3 different types of files, depending on if I'm going to use that data within the run, whether I'm going to be looking at it while the application is executing to make sure that everything's happening the way I expect, or if it is a file that just needs to be written such that I can do my analysis later. And those 3 different categories, or those 3 different axes, lead me to 3 different ways of writing data. And I'm going to go through each of these in kind. But to summarize them first, anything that I use for monitoring while the program is executing, I write using the logging library in Python, such that I can easily read in English sentences what is happening, making it very easy for me to monitor and kind of get an idea if everything is working the way I want it to, i.e. if I need to kill the job and go back to the drawing board. Now, logging is great because I can read it very quickly as it's scrolling across the screen, but it's annoying because it is written in a human language, which means I have to write my own parser for how to turn it into machine accessible data. I can write text files instead, like CSVs or JSON files, that I can read easily from the machine in those cases where it's not necessarily data that I'm going to be watching it scroll across the screen, but it's going to be something that I know I need to read later very easily. So I tend to write text files. I like CSV if I can get away with it because it has less bloat than something like a JSON line delimited file. Last are those things that I track during the run that I may actually use later while the program is executing. Like, say I'm simulating a bunch of materials, I may pull that data later to be able to train a new machine learning model. And in those cases, I don't want to read from a text file on a high-performance computing system for a few reasons. First of which, text files don't do very well if something is writing to that file while I am also reading it. You can get around that limitation, but it's annoying. Databases, on the other hand, like if I'm, say, running SQL, I tend to run MongoDB, allow you to both read and write concurrently, which solves a lot of the problems of text files. Additionally, you don't just read and write from them concurrently, you read and write from them very quickly. All of this is at the expense of the database is something that requires software. You cannot read it as a human. So it's something that is definitely not for on-the-fly monitoring of the workflow system. So with these 3 kind of examples, I'm going to show you how I do them in software and what that data looks like and how I can analyze it later. So let's start with logging. So going back to the code, we're going to scroll down a little bit and show you how I set up the logging. Now, I use Python's built-in logging library. I'm sure there are some nice attachments on top of it that can handle some of the peculiarities. For instance, the way I have this written, you can see here, I write all of my logs to the same standard out file, which means I do have to separate them out from each other when I'm reading it. I may take the file that's being streamed to disk, run that log, and I might use a filter operation on the Linux command line to print out, say, only messages belonging from a certain entity, which is tedious. There are probably some better ways of doing it, but I find this pretty simple to set up. And the key bits of it here are: one, I define my ways I want my logging to be handled. Now, a handler, and I'll point to the documentation from the Python standard library, comes in a few different flavors. I have one that prints out to a stream, like the standard out from my program, and I have another that writes to disk. And you'll note I give it a path to my nice and convenient run folder. What I then do is I take only a few of the loggers. Now, one thing important about Python loggers is there are a tree of them. Now, to explain the tree, well, let's go take a look at one of my logs that are available. Oops, clicked the wrong screen. Let's go back to, how did I not download the logs? Okay, I surely have downloaded one from here. Yep, here we are. So let's take a look. You'll note that for this particular instance, this logging line here comes from a so-called sublogger. You'll note that the logger has a multi-part name. This here defines which logger it came from. This one came from the logs associated with my main program, belonging to the Mofa thinker logger within that program, and more specifically the submit generator logger from even within that original logger. Now, if we go back to the setup of my logging function, you'll note that I didn't actually get all of those specific granularities of loggers. I only grabbed this thinker.logger, which happens to be the Mofa thinker logger. So what I'm doing is I'm implicitly grabbing one, like the highest level logger that I care about, and it will implicitly get all of the ones underneath it. Now, the key point here is I'm not grabbing the root logger, the thing that sits at the bottom, and every Python module or every sublogger uses. It's called the root logger. If I do get logger root, I'm going to grab that one, because that's going to be like way too much information. Any of the sub-libraries that I'm working with, I don't know what their logging messages mean. I may not necessarily care about them. So I'm opting not to have them printed to screen by picking, to reiterate, only this main logger and only one specific logger, this thinker.logger that I have available. So once I have those, again, I'm plucking little sub-loggers, branches from within this larger tree of logging messages that are getting written. I take each of them, I write them in a format that I find aesthetically pleasing to two different sources. One goes to standard out so I can see it while it's getting run. The other's getting into a run log, and I flag them at a certain level each. I only get info. I don't go down to the finest granularity of debugging. So that's it. That's how I do the logging. And that, as we alluded to here, gives me a long stream of different tasks which I can watch to say, make sure that my retrain operation started. I can see that at 3 o'clock in the morning, about a week ago, my train started happening. I could see within 100 milliseconds, I had already grabbed the training set from disk by, it looks like, so here's 21 seconds. Well, we're going to have to go through and show a little bit more than I thought. It was 17 is when that started. By 27, so 10 seconds later, the model had finished training. Small data set size, it takes longer once we gather more data. You can see that everything's kind of happening as I expected to. And 50 milliseconds later, or 70 milliseconds later, we have gathered the next training set size and it's gone off again. So this logging, hopefully you illustrated here with me sort of talking through what's happening in real time, allows me to in real time understand if this application is working as I'm watching it to get ideas. But it's not something that I want to go and analyze because I wrote these for human understanding and not necessarily machine. Now, machine happens a different part in the software. And as I alluded to earlier, going back to this handy notes, the other thing that I want to do to write data that I'm going to analyze later, and I don't care if I can read it while the program is executing, goes to ASCII files. I like ASCII files because I can read them in a text editor and understand how they happen to be formatted relatively easily. And those will give you an example. We'll go to the retraining code that I just talked about. Let's take a look. So here's the retraining function. One thing I didn't mention earlier, the logging function. Here I'm writing to a specific sublogger. If we go back to the code, the run log, we can see there's a logger that happens to be named bopathinker.retrain. It's this object here. I'm writing info to it. That means a logging message is getting emitted at a certain level of priority. So you can see here, I've got a lot of different logging messages that are coming out, and I've written them in ways that hopefully should be self-explanatory to people reading the logs, especially if they're not me. Now, the other thing that I mentioned that I read, going back to the subject of this, is I write to text files. So here at the end, I've got a particular bit of data that I know I want to analyze later, which is the retraining result object. That contains a lot of information for me, like the time that retraining object was started, the time it actually arrived on a compute node of the supercomputer and began executing, how long it executed for, what size of data it produced afterwards. This is all a rich amount of information, more than I'd want to translate into an English sentence in order to express to screen, but is exactly the kind of thing that I need to analyze later. So here I'm going to write that to a JSON file. The way that I do that is I print to a file, your standard Python print command, and I write to a specific output file. Now this looks a little bit convoluted because I did some optimizations here. We're running at pretty large scales, so I want to make sure that I don't reopen the file more than necessary. So what I do is I hold on to all of the open files that exist that I'm going to use through the life of the program in a little Python dictionary, such that they are created at the beginning, they're never closed. Closing and opening causes an inefficiency. And at the end of the day, when I'm finished with all of those files, I can seamlessly close them because they're all stored together. That's a bit of an optimization. We don't have to care about that. The only important thing to know here is I'm writing to a I'm writing to a file in a JSON format such that I can read it into pandas later. So here I've got my JSON file. It's gross. This is not the way I'd want to read it as a human, but I've seen a lot of these, so I can understand a little bit on what I'm looking for. Like, this is the time step at which the run was created. I can see it launched at 243 milliseconds by 245, so 2 later. It had been received by the workflow engine, and at 964, so 700 milliseconds after that, actually, sorry, that's 6 seconds later, it had arrived on the compute node. So here you can see I've got the information that allows me a very fine level of detail, and I can write software against that. So I can write, say, software that plots my runtime utilization by looking at the time where each of those tasks began and ended. I'll show you up here. Here I'm reading in from those files. I'm pulling in those timestamps that I just showed you out of a JSON file pretty quickly. I can pull that data in, and maybe this looks like about 20 lines of code to be able to pull out the information that I need, and can then string it together to make plots. So that's the second type of file. Doesn't have to be JSON. I also write to a CSV file as part of this code. I've got a function where upon a set of molecules arriving, I want to keep a persistent record of all of the molecules that I've created. So I use Python's dictionary writer to write this is from the CSV library, to write a CSV file to disk using a list of dictionaries. So here I take the records of all of my molecules that I've created. I know it's a list of dictionaries, and I write them to a CSV file that I can go and analyze later. All nice and simple. So that brings me to the one that's the most tedious, that's a bit hardest to work with in terms of being able to write to it and to read to it later, which are databases. Now, databases, as I mentioned, are great. As we discussed earlier, they allow concurrently writing to them and reading to them from multiple processes that can either be all together on the same node, they can be on different compute nodes from the supercomputer, and I can do it in a way that all of that data is written automatically to disk, such that I don't have to write my own process to monitor and make sure everything is logged at the end when the run eventually finishes, that I have to make sure it's persisted. All of that is done for me very nicely. But this is going to take a bit of software to work with because it is inherently a computer program we're talking to. So I'm going to show a little bit on how that's done. Talking about databases is something that is certainly not I can do in just the short video here, but I want to give you at least a quick splash on it. So let's talk about this process MD results function. This is the first time I write a result to the database, and let's talk about what it is. So at this point, I have finished one type of simulation that I use in my application, MD, Molecular Dynamics, and I want to write it to disk. I want to be able to persist that data such that I can both see it later after I've run this high-performance compute application and during the run. I want to be able to train a model on this. So here I have created a database object. This collection object is from PyMongo. It's a tool that allows me to work with Mongo databases. And I've taken my record, which is a Python object describing the molecule that I'm working with. I've got this whole data class called a moth record that I'm working with. Oops. We'll see if I can. All right. We won't talk through the data structures here, but you can think of it as just a big dictionary. And I'll take it and I'll write it to the disk. Here, I've hidden the actual Mongo related things. That's not as important by me showing you later that now that I've written to this database, I could say, write a query to pull from it later. So here I want to find the molecules that had the best property that I've read through. All right, we're back. My spouse just got back from a walk, so I paused so I could chat with her briefly. But what we were talking about was, now that I've written all of this data to disk into a database, I can write easy queries against it. I'm using PyMongo again. This is not code that I had to write, which is one of the advantages, where I can just express a query like, sort my available materials by their stability. Don't return the long list of coordinates that I have stored in the database, but do sort it by stability and return the top values. Because it's in a database, actually writing this query is it's really only one line of code that I've split out just so it's easier to read. But in short, very simple. And if you remember from me talking through the logs, I explained, oh, I just read the data and looks like 20 milliseconds. That's fast because MongoDB is very quick. I can read from it later. I write data to it in some other portions, like in this case, after I finish computing the gas storage capacity, I store that as part of the record as well as the time that it completed, allowing me to analyze it later. In this, I can both pull back out if I say wanted to train a machine learning model not on the most stable materials, but on the ones that stored gas most effectively. I could do that too. So that's how we work with the database. How we analyze it after the run, because it's in a binary format, takes a little bit more effort. You have to run what eventually happens with one of these files, and I'll pull up a run. So Mongo writes a bunch of files on disk that make sense to Mongo. In order to read them, you have to run a server to be able to interact with these files. I find that tedious. So what I do is I write a little script that launches a service for the extent of time that it takes me to export that data to a JSON file. So in this way, at the end of the day, instead of having to run a service and interact with it, write queries against it and analyze the data, I just dump it all to a JSON file that, if we go back here, I can go and read from. So here I'm reading from that data file. You can recognize those fields that I was using to query against. They're all written nicely here. So I've got all of that data, and I can create my plots without ever having to care where the data came from at any point. So that's the long and the short of it. We'll go back to the beginning real quick to summarize. There are two things that I do when setting up these high-performance computing runs. The first of which is I assure they're all isolated from each other. I don't edit the Python file. I use an arguments parsing library called argparse built in with Python. Once I read in those arguments, when I start the program, I ensure it gets its own run directory where everything down to the database is stored together such that I can analyze it easily later. And those files that I write, I do in a few different methods. I use Python's logging library with using the logging stream handlers to write to that output directory that I've created all of the logging messages that belong only to the parts of the software that I care about. Remember that notion about subloggers. I write text files for things that I'm going to analyze later, but are too rich of data to express in a logging message. And for those data which are, say, going to be reused during a run or are generated in sufficient volumes and speed that writing to a text file could become problematic, I write those to a database. And I read from that database while the program is executing, but I have a short script that writes them out to a JSON file at the end, just so they can become, like these text files, things I can read in a text editor, read in through pandas, and be able to create my analyses easily afterwards. So that wraps it up for today. That was a lot to talk about for this particular part of the software. I've got more things from this application that I either learned or was able to remind myself about while building it, and I'll write some videos about those later. So hope you're having a good day. Take care.